Welcome to the Namena video tutorial. This lecture is the first of the CSP Technology block and will give an overview of CSP Technologies. Let me introduce myself. My name is Mark Röger. I studied engineering and have a PhD in mechanical engineering. I've been working with DLR in the CSP field for over 13 years. To begin, I have a brief remark on the difference between PV, photovoltaic, and CSP, concentrating solar power, followed by an overview of the different CSP technologies. Then I'm going to say some words about the different efficiencies of concentrating solar power systems. I will conclude with some remarks about electricity costs. We can distinguish technology-related costs and energy system-related costs. In photovoltaic, the sunlight is directly converted to electricity using semiconductors. The photons create excited electrons and remaining holes, which are separated, and hence a voltage is built up. The principle in concentrating solar power is totally different. Here you see a collector. In concentrating solar power, heat is produced by concentration and absorption of solar radiation. Here you see the sun rays impinging on the mirrors, which concentrate the light on the absorber tube and where the heat is produced. This heat can be used similar to the heat produced in a fossil or nuclear power plant to drive a turbine and generate electricity. In contrast to PV, there is the possibility to store the heat economically in a thermal heat storage before transforming it to electricity. Let's have a look how we can concentrate the solar radiation. 4 basic types of concentrating collectors can be distinguished. The most widespread and commonly used concentration technique nowadays is the Parabolic Trough. It is a line-focusing technology. Here you see a photo and a sketch of a Parabolic Trough collector with its receiver in the focal line. The radiance is concentrated by a parabolic reflector. The receiver is located in the focal line of the mirrors, and the heat transfer fluid is heated up to 400 degrees C. Normally, Rankine cycles are used as a power cycle. Using other fluids than oil, as for example salt or steam, we can even reach higher temperatures. It is a single-axis tracking system, and nowadays plants up to 80 megawatt electric have been built, and plants with 280 megawatt electrics are being built. It is the most major CSP system. To resume, parabolic troughs are one-axis tracking technology. Its concentration factor is about 80. That means on the solar receiver we have got 80 suns. The temperature range is between 200 degrees C and up to 400 or even 500 degrees C. The power level is between 50 and 280 megawatt electric. A second, also linear concentrating technology is the linear Fresnel collector. You may all know that you can concentrate the sun using a magnifying lens. Fresnel lenses are special flat lenses which reduce the amount of material required by dividing the lens into a set of sections. A Fresnel lens and sun rays are shown here. At the bottom you can see the focal point. If you use mirrors instead of a lens, we can place these mirrors near ground level and the focal point is located above. This configuration is used in a Fresnel collector. So the Fresnel collector is a line-focusing system. The receiver is fixed and only the primary mirrors are tracked. A secondary mirror is mounted above the receiver tube so that rays not hitting directly the receiver tube are redirected towards the receiver. Compared to a parabolic trough, we have got lower investment costs but also lower efficiency. Process parameters and plant capacity are similar to those of a parabolic trough collector. Commercial plants up to 30 megawatt electric are being built. To resume, linear Fresnel collectors are, as parabolic troughs, one-axis tracking and have similar concentration factors, temperature and power ranges. A further system is the solar tower, also called central receiver system. In contrast to the before-mentioned line concentrating technologies, it is a point-focusing technology. The irradiance is concentrated on a central receiver by heliostats. These heliostats are two-axis tracking and have a mirror area between a few and 150 square meters. In a solar tower, we get higher operation temperatures due to higher concentration ratios. Besides the Rankine cycle, also the gas turbine cycle is applicable. Up to now, commercial plants up to 20 megawatt electric exist and several plants around 130 megawatt electric are being built. To resume, solar towers use two-axis tracking heliostats. They reach higher concentration factors of about 200 up to 1000 suns and hence reach higher temperatures between 600 and 1100 degrees C. The power levels are in between 10 to some hundreds of megawatt electric. A last CSP technology I want to mention is the dish system. The parabolic dish is a two-axis tracking technology where the receiver is mounted in the focal point of the reflector. It is often used in combination with a Stirling engine, then its capacity is limited to approximately 10 to 25 kilowatt per unit. It is more for small or medium-sized installations, either in off-grid or in grid connection. Here we see all the four concentrating technologies, and to resume the dish system reach quite high concentration factors, over 1000 or several thousand suns can be reached. Using a Stirling engine, the temperature is about 700 degrees C, but we can reach until 1000 degrees C if we use microturbines, for example. The power level is smaller compared to the other technologies. Let's come to the next section of this lecture. Why do we have different concentrating technologies? Which technology is best for a specific purpose? In the first step, we have to convert solar radiation into heat. So solar collecting systems may work with low efficiencies at temperatures they are not designed for. The thermal efficiency is defined as the ratio of what you get out and what you put in. The solar thermal efficiency hence is defined as the heat flow we get out and the solar radiative flow. So imagine you have got a flat black plate on the sun and you can reach temperatures only below 100 degrees C with a quite poor efficiency if you want to get out the heat of this plate. If you want to get out heat at lower temperatures like 30 degrees, we may get out the heat with a higher solar thermal efficiency. This type of collector has no concentration, so the collector concentration is 1. If we now get to higher concentrations, like 10 or even 70, like the Parabolic Trough, we see that we can reach temperatures of about 400 to 500 degrees C with still high solar thermal efficiencies. And if we get to the solar tower or the dish technology, we even get higher temperatures with high solar thermal efficiency. So to conclude, we can say only collectors with high concentration factor C are suitable to generate high temperature heat. In a second step, the heat has to be transformed to mechanical energy. Thermal energy has got different quality depending on its temperature. So the definition of thermal efficiency is the same as in the slide before. And the cycle thermal efficiency here is defined as the mechanical power we get out to the heat flow at temperature T. The maximum cycle efficiency an ideal machine would reach is the Carnot efficiency, which is plotted here. We see at higher temperatures we can get higher Carnot efficiencies. Real machines don't reach its theoretical limit and have lower efficiency. A Rankine cycle would have efficiencies between 38 and 45%. A combined cycle would reach efficiencies up to 58%, but requires higher temperatures of about 1000 degrees and higher. So high cycle thermal efficiencies require high temperatures. Finally, the total system efficiency counts. It is the product of solar's and cycle thermal efficiency presented before. The total system efficiency is defined as the ratio of electric power and solar radiative flow. We can observe that the efficiency lines have an optimum. With a non-concentrating collector, we can only reach marginal total system efficiencies below 5%. With higher concentration ratios, we can get higher temperatures with higher total system efficiencies. Higher temperatures and higher efficiencies in this direction. Solar towers and dish Stirlings provide a high potential of high total system efficiencies. For example, Sandia and SES set the solar to grid system conversion efficiency record by achieving 31.25% net efficiency rate during a cold winter day. In the last slides, I have talked about efficiencies. However, the parameter which mostly is decisive for a power project is the electricity generating cost. More precisely, the levelized electricity cost. It is the ratio of total annual costs and annual electricity produced, which we can express as euro or dollar per kilowatt hour. We can distinguish between technology-related costs and energy system costs. The cost figures should both include external costs. Examples for technology-related costs are, for example, the LEC for a specific PV project, a specific wind or CSP project, or even for a fossil or nuclear power plant, and so on. In an energy system, we usually have pronounced generation and load profiles, so the weighted sum of the technology-related costs and transmission costs not necessarily lead to the overall energy system electricity costs. So not only the technology-related costs, but also the energy system electricity costs should be minimized. For example, at points of time with a high solar share of renewables and low load, this may lead to curtailment of intermittent renewables. For this reason, in addition to load management and smart grids, energy storage systems are required. The CSP technology has the inherent advantage of storing energy economically in a thermal storage. Here you see an aerial view of the 3 Andasol plants, each having 50 megawatts. Each plant has got a thermal storage allowing 7.7 hours of full operation. You see here the cold and hot tank. By using CSP with storage, the grid flexibility increases and the share of renewables in the energy mix can be increased without curtailment of renewable energy. Hence, CSP with storage can reduce energy system electricity costs. Here we are at the end of this lecture. Thank you for your attention.